Okay, welcome. So this is Stephen Creech, and today I will be telling you about my paper, Extensions of Hyperfields. This video will just kind of go over the introduction and the main ideas of the paper without going into any details. Perhaps before I get started, I just want to give a thank you to Professor Matt Baker at Georgia Tech, who kind of advised me on this project that I worked on back in 2019 and kind of guided me through writing this, as this was my first paper and first sort of research project that I did. So I will tell you the idea of the following is we'll start off. Why? Okay. We'll start off with two sort of worlds. There's sort of the world of fields, and there's this world of hyperfields. And I am making the assumption that you know what a field is, kind of from an algebra course. In hyperfields, they're kind of like fields, but the word hyper here just means multi-valued addition. So when you add two elements together, instead of getting a single element, you can have multiple elements. And we will give examples of this. And so let's start with some classical field theory. The classical field theory says, well, let's say I have f is some field, and I have some polynomial little f of x in f, and I'm going to assume that little f has no roots in big F. So kind of an example of this would be something like x squared plus 1 in the real polynomial rings. So here my field is the reals and my polynomial is x squared plus 1. So we don't have any roots to this polynomial. So then the question is there an extension of fields? So something like L is an extension of the field F, such that little f has a root in L. So kind of the question of, can we find roots? And the answer for our example here would be yes. And I can remind you of the construction. So here, the complex numbers would be the answer. But the way you really want to think about the complex numbers is we take our polynomial ring and we mod out by the ideal generated by our polynomial with no roots. Well, really we want an irreducible part of the polynomial with no roots. And in doing this construction, we can find roots, or find an extension with roots to our polynomial. So sort of the first question is there an extension with roots? And kind of the answer is yes. So what happens in the hyperfield case, so in this paper I tend to use capital K for a hyperfield. So I have some hyperfield K, and if I have a lowercase k is some polynomial in the hyperfield, and I believe I use the variable t for the variable associated to a hyperfield. So I have a hyperfield, I have some polynomial, whatever a polynomial means, we will define this later, and little k has no roots in our hyperfield K. So exactly the same setup, and we can ask the same question. Is there a hyperfield extension such, maybe I think I still use L over K, such that little k has a root in L. And what we'll have to do is kind of define what we mean by extension, because addition's multi-valued, so there will actually be two different kinds of extensions, depending on what we determine is inclusion of sets versus equality of sets for addition in the extension. So that's the question, and the answer is, well, yes, but no. For a general hyperfield, this is still an open question, but we construct this for what are called quotient hyperfields. We can extend. And that is the first of our two main results. There is sort of a kind of hyperfield called a quotient hyperfield, which we'll define, and we can do a construction to get a root of a polynomial which has no roots. So this is sort of the first result, and sort of going along, we can continue. The second thing that one might ask is minimality, right? So in our field case, if f is a field and little f has no roots, well, in big F, but let's say we have some roots, and in kind of some extension, and I don't know why, I just thought it looked cool at the time, but I considered a xi, which for the variable I would use as a root, which looks nice, however, I have trouble saying and writing it down, that variable. So f is a field, f has no roots in f, but c is a root of little f. Then we can construct the field f adjoin c, and this is the smallest, so this is the smallest extension of capital F containing the root c. And a classical result is this field is unique up to isomorphisms. So such a field has to necessarily be unique. You have sort of this smallest, you have a minimal extension containing a root. So here we can ask the same question. Let's say K, well, I don't know how to extend a general hyperfield, so let's just say, well, we can still ask the question, if K is a hyperfield and little k has no roots, in K, or in capital K, I need to erase, but I have some root c is a root of little k, then can we define sort of the field k adjoin c? And perhaps the surprising answer to this is no. K adjoin C is not a well-defined object. And kind of the second main theorem of the paper is really to show this is true. And this is neither in the weak or strong sense of extensions. So what we do is we give an example of a hyperfield and a polynomial over the hyperfield, and we will actually construct two different extensions, which in some sense are both minimal in that they don't contain it. There is no other one containing this root. So, but they're not going to be isomorphic in either sense of the word. And so this is sort of the main results of the paper. And yeah, so this is the first section. Perhaps I will do a quick outline of the rest. So this is just section 1. So section 2, this is going to be our preliminaries. So in this section, I will define hyperfields. So this will be what are hyperfields with examples, lots of examples. What are the quotient hyperfields? I believe I do in this section. Yep, quotient hyperfields. Again, we'll see the same examples, but now as quotient hyperfields. We will do hyperfield extensions, both in the strong and weak aspects. And I believe, yes, we finish off with what are polynomials and roots over hyperfields. So this is sort of the main crux of getting down all the terms we need. So that's going to be section 2, so that will be the next video. Then section 3, this will be sort of the first of our two main theorems, so sort of this for quotient hyperfields we can extend. So this is, we call this strong extensions for quotient hyperfields. And then the last section, section 4, is going to be kind of this minimal extension is not well defined. And that is going to be the crux of the entire paper. And yeah, so if you stick with me for, I guess, 3 more videos, we will kind of go through the rest of this. All right, thanks for watching.